So welcome, thank you for joining us one and all. I'm Gavin Clark with the National Museum of Computing. And I'm here, my pleasure to welcome Yurii and Alex here this evening, who have lives, but we know them primarily, I think, for the Software and Computer Museum in Ukraine. That's how we came into contact with them. We are going to be discussing an interesting chapter in modern computing history this evening. As you well know, the National Museum of Computing, one of its core remits is to tell the story of the British story of post-war computing. But of course, you know, that's one aspect of what happened after the war. Computing was blossoming in many other countries around the world as well. And of course, we hear a lot of common stories. Many of the names we're familiar with: EDSAC, ENIAC, Manchester Baby. But at the time these systems were coming to fruition, there was, of course, a larger event taking place in the world, and the Cold War was kicking off. And that meant for mathematicians and computer scientists on the wrong side of the Iron Curtain, they were very much cut off from the, I suppose you would call it, the intellectual and the engineering beltway, the scene, the cultural circuit, the cross-pollination of ideas that were taking place in the West. So and yet they produced, one particular group in particular in Ukraine produced this amazing computer, which is regarded as Europe's first digital computer. The name of which I'm not even going to try to pronounce in Ukrainian, but which I'm reliably told translates as small electronic calculating machine. And from what I understand, having read the stats, there ain't nothing small about this machine. 6,000 vacuum tubes. If you compare that to Colossus, which had 2,500. Capable of 3,000 operations per minute. Quite a fascinating achievement with a strong, interesting story in there, particularly for some of the work that was accomplished using that machine. And also it has a strong, there was a strong role of women involved in its use of that system too. Yurii and Alex are going to take us on a journey through that this evening.
Hi, dear ladies and gentlemen. YouTube. Remember this day, remember this moment, remember this great person to all your life, told my mom to me in 1965, drinking a tea at our home with family friend, Sergei Lebedev. Of course, I did, as you see now. My name is Yurii Yushchenko. I teach computer science at the National University of Kyiv, Mala Academy. I have Ph.D. in math and physics sciences. Also, 5 years ago, I started researching the history of IT. As you are here too, probably you are close to IT or the history. Thank you for your interest. We appreciate your time and will try our best to share the truth as much as could discover it. So let's travel in time a bit to 1949. In Kyiv, in Ukraine, the first Ukrainian and USSR computer, complete by Turing and using von Neumann-Lebedev principles, was built. It works in 1950 with 6,000 lamps and 3,000 operations per minute. By why its importance and influence were hidden? Not like its brothers, Manchester Baby, EDSAC, or EDVAC. We will talk in Ukrainian mathematicians' role about communist mode role in the recognition of loyal ones. And we will see how design limitation inspired ideas to build the whole USSR generation of computers. We will provide reasons and results. Thank you for your interest about an interesting story of MEOM computer with very important and unknown its heritage. Oleksandr makes research for the future film. It is about people who started IT in Ukraine. He will present the main part of the presentations. Let's go, Oleksandr.
My name is Oleksandr Bezrukavyi. I am a Master of Computer Engineering from Kherson Technical University in Ukraine. I was trained to project computers in 2000 and so on. I was doing projects on computer automata like Mila Mura and so on. So these hardware things, they were with me for 20 years something. As well, I'm interested in people who are doing great things and their ideas and their history. That's why we met with Yurii and now sharing this story. I would like to say thank you to the National Museum for this opportunity, for making this open for English-speaking world, and as well to thank to the British government for supporting Ukrainians and their humanitarian needs, as well as the European government supporting us in this time, and to Ukrainian soldiers staying on the line. So we have this opportunity now to present this to you. So let's go. To understand why this computer created, let's go a bit in the story back. We can start asking some questions like, why did Sergei Lebedev, exactly the engineer, was the initiator and the leader and the chief engineer and the MEOM, we would say in Ukrainian, MESM in Russian. So we will continue Ukrainian notation in MEOM development. What did he do before he began working on the computer? What motivated the creation of a complete, Turing-complete digital computing machine in 1950? During World War II, Sergei Lebedev worked developing electronic systems for stabilizing tank gun size and analog home systems for air defense targets. In 1945, he created the USSR's first analog computer used for solving problems related to energy calculations. After reading about Alan Turing's universal machine, Lebedev wanted to create the universal machine that is capable of solving any mathematical problem, not the just specific differential equations that he needed for his electricity calculations. What pushed Lebedev to create a full-fledged digital computer was a series of just advertising articles he could get access to. These articles described just capabilities of computers his friends had bought abroad. However, those computers couldn't get the programs in their memory as advanced as the Turing concept. While working in Moscow, Sergei Lebedev faced challenges in bringing his ideas to life due to limited opportunities. He was very young, a doctor of sciences, very successful, and many competitors didn't like him to be in the capital Energy Institute, going with unknown, unpredictable costs for something who knows what. So with the help, as the story tells from some people, of Lebedev's wife, who connected with her friend, the wife of the Stalin right-hand Marinovsky. That lady was the director of the Energy Institute, and she assisted in transferring Lebedev from Moscow to Kyiv to continue his work at full. Sergei Lebedev officially accepted an invitation from Mikhailo Lavrentiev to relocate to Kyiv. There he found better opportunities to pursue his work. Interestingly and independently, as many people believe, of von Neumann, just using Alan Turing's description, Lebedev developed same principles of building a complete, Turing-complete digital computer. However, this happened because von Neumann principles hadn't yet been made public at that time. You can see photos of several engineers now on the slide, and of them we will trace forward a couple like Lev Dashevsky, Katrin Shkabara, Semyon Pogrebinsky, and Zinovy Rabinovich. Those engineers had not an easy path to get to the team. One was Jewish, so there was a limit for a number of Jewish engineers on any project in Soviet Union, kind of. So in order to prove that you can hire a second one, you need to prove that he's not Jewish. So there was a Communist Party meeting saying, like, that guy was baptized in Christianity. That's why we can accept him as not a Jewish, kind of, as a Christian. So kind of overcome the artificial quota of this religion. And then it wasn't like the big university or big organization and you just switch to the project. One of them found advertisement, like they need electrical engineers for the project. So he just get the job. It wasn't like a military project. Let's go to the dates and let's see how it was going. The development progressed as follows. From August 4, 1950, trial runs began for the debugging after completion of the control panel. On November 6, 1950, mathematicians watched the performance of machine on various programs, including solving simple differential equations. Demonstrations of MEOM's functionality occurred on January 6, and it was for capital Moscow mathematicians to show capabilities of already running machine. On December 25th, 1951, the government commission accepted machine for operation, and forward documentation was ready in January 1952. So by January 1952, mathematicians at the Institute of Mathematics in Ukraine started using this machine after being trained with documentation only from the spring of 1951. Then later, in 1953, first printer was added for printing data and programs from its memory. These details was recalled from the memory of people. In 1954, computer and developers were transferred, they became the responsibility of the Institute of Mathematics, not just the laboratory of Energy Institute in Ukraine. The support that Institute provided, it stopped in 1957 as the more advanced machine Kyiv became available, more reliable, more faster, and better architecture and better ideas. So there were no needs any further to run more slower, more headache machine because of the reliability. In 1959, parts of this machine were moved to the Technical University in Kyiv for educational purposes, not for running it as a machine. And later was kind of secretly transported to Kryvyi Rih Mining Institute for educational use because there was an order to kind of dispose it. There is a reason Lebedev and his team kept the development of the computer kind of secret between 1948 and 1950. That was even not labeled as a top secret, the first Soviet machine, because the government was there. It was only after they successfully demonstrated that the machine is running in 1950, they released the project and got funding next year from Moscow. So he discovered von Neumann principles, and unlike a kind of Moscow counterpart, the Moscow M1 computer being created at the same time with support, the MEOM had unique features because the development team couldn't obtain detailed information from Western computers due to the lack of kind of support from the capital, from Moscow. Instead, they relied on general information and advertisements and magazines. So the team of nearly 10 engineers, then later increased to 20, started the project like in the garage area. So it was like a startup. Conditions of first creation were not comparable with many foreign computers, which were financed by even military or much larger organizations. In 1948, Sergei Lebedev started designing this machine, naming it a model of electronic computing machine or the maquette. He intentionally didn't use the word like it's a real machine. So it was just, you can imagine, like the model of the, let's say, railways with lamps and rails and everything. So just a toy for modeling something. So you could explain to the Energy Institute management or the Mathematics Institute management that let's say modeling, solving the electricity problems. And here you can see that the engineering mind, like from the real task, not Enigma-like or calculations for atomic bomb, they were calculating paths for electricity lines between Moscow and a powerful hydroelectric plant. And there were like stability and other equations, and they required a lot of calculations. So the mind was obsessed how to solve a lot of calculations and there find the truth. And organizing the seminar, Lebedev invited famous mathematicians, very open-minded, including Boris Nedenko, who suggested increasing the number of bits of storing numbers from 11 to 17. So that would give like 5 significant decimal points to ensure accuracy for mathematical calculations. And Mikhail Lavrentiev assisted in securing the building for the laboratory involved in MOLM development. So it was just, you need to find the garage, you need to find the details, you need to like bring your idea alive in the post-war country where everything still was recovering. The laboratory for MOM development was situated in the kind of ex-hotel for church visitors in the village Theophany on the outskirts of Kyiv. The building, two-story, once was a psychiatric hospital before the war, and a German hospital during World War II. The employees of the laboratory, consisting of 10 engineers at the time, had to renovate the building themselves. So you can imagine mathematicians or engineers have high qualification making construction works for their building. They found just wooden tables and chairs. That's kind of old furniture. As well, Theophany didn't provide public transportation, so workers relied on the service bus that should bring them to the work morning and back to Kyiv in the evening. Due to the stability issues, you can imagine that, let's say, 200 hours and the lamp would be kind of not working. And the power stability that was required for the machine, so during daytime, the electricity, let's say, frequency and power wasn't stable enough. So most important calculations was scheduled for night shifts. Then everything else wouldn't disturb the electricity, and electricity wouldn't disturb lamps, and lamps wouldn't spoil zeros and ones in this story. And Sergei Lebedev himself worked in this building on the second floor. He has a bed linen to rest after working days, and the residents provided rooms for laboratory workers. You can see details that now is obsolete, like tubes, the professional audio devices probably, and I don't think you can find them anymore unless it's amplifiers. So the development of the computer wasn't only physically separate from other projects worldwide, but it was happening concurrently with another machine. So this separation helped to conceal the originality and unique architectural features of the MEOM, which we'll discuss later. Unlike other computer projects financed with state funds, the team involved in this development were, we could say, 10 times fewer than another similar projects. And due to the lack of funding, there was a lack of details. Some developers mentioned that they managed to find necessary resistors and capacitors on the landfills of the military enterprises, and they bought the necessary vacuum tubes at their own expense on the radio market. As well, we could buy on the radio market vacuum tubes for military purposes. The main operations that were projected or deployed. Of course, addition for the subtraction, multiplication, division, shift, multiple types of comparisons, unconditional transition, data exchange with magnetic drum for storage. It was a revolutionary thing, actually. Special command, addition of commands for working with arrays, such as setting commands for looping operations. This is a unique command created by them and different from other kind of wartime machines. I will pay much attention to it, and it is mentioned in some literature sources. So, and of course, the stop command. These operations allowed MEOM to execute different computational tasks and processes efficiently. Let's look at the characteristics. The arithmetic device is parallel operation pioneering this method in the world. As we suggest, a number representation was fixed point numbers. The command system employed free address command structure. The random access memory utilized triggers with 31 triggers for data storage and 63 triggers for commands. You can imagine triggers as 2 lamps, big ones. So it's just one bit. You can imagine 8. So it will be like 16 lamps, 1, 2, 3, 4, 16, like a row or the box. So it will be actually modern bytes, but those times we didn't use bytes. And permanent memory stored in plugs. So you could see stackers in other machines worldwide. Here we use plugs, connecting contacts with 31 plugs for data and 63 plugs for commands. The frequency was 5 kilohertz. The processing speed around 50 operations per second. We have seen many literature sources saying like 3,000 per second. So let's just multiply by 60. It was 3,000 per minute. And 6,000 lamps, of course, yeah. And you can imagine the cost of replacing them. If you have reliability for the lamp very limited. You can imagine the work engineers were doing, running around with lamps and trying to diagnose and find everything and replace it. And then machine stops, and so on. And then if the lamp is not that much reliable, the calculation need to be done twice. So the machine runs twice. And you would see that the power consumption is 25 kilowatts of power and 60 square meters is the physical area. So you can imagine how pioneering and innovative nature this computer was for its time. It was less power consuming than some other first and second machine in the world. Let's go further. Some features of the architecture, of course, parallel arithmetic device, and the second is dynamic modification of programs, addresses in them. This is common for alien commands, CAC in English, but this unique command that brought the idea of pointers later. The MEOM computer utilized the library programming approach with 2 counters. The division of RAM was for 2 parts, tubes and tumbers of plugs. Central control counter was used for the main program and stored address of the current command being executed. And the second, local control counter, was responsible for managing subprograms. This counter stored the address of the current command during subprogram execution. So the architecture suggested only one level of depth for subroutine, and what was kind of architectural limitation, and later it was the reason for generating a new breakthrough idea. Let's look. Now you'll be afraid of the formula. It is just a calculation that shows that you have a function to the left and some functions to the right. And then if you need to calculate it, you need to have an option to run the function from something as a parameter as well as a function. So you go to the depth of 2 of subroutines. So there was a presence of the ability for one subroutine to call another subroutine just one main program to call one subroutine. And another subroutine couldn't be called from subroutine and forward. So that means calculating sine, cosine relieves like programmers from unnecessary effort and reduces the likelihood of making errors, as well that allowed to take less computer memory. Now, in modern programming languages, we can have constructions much deeper. And by that time, that was the first machine, and a lot of calculations were done just with these capabilities. Let's examine the fourth feature a bit more, the division of RAM into two parts, tubes and Tambor's plugs. It was a significant innovation utilized in the MEOM computer. This concept was later refined and incorporated into the Kyiv computer in Ukraine. Furthermore, this division served as a catalyst for the development of addressing mechanisms such as pointers in higher-level programming languages. Pointers play a crucial role in modern IT, as we know. They allow efficient memory management and data manipulation. Indeed, pointers have become indispensable in modern computing. So that's fascinating to find how it all started. Let's look at the first task we were doing. So in order to understand what was first tasks, Sergei Lebedev itself was calculating power lines from hydropower plant to Moscow. So it was a lot of equations. So as he created machine, his tasks were on that machine first, kind of. Further, you can imagine one machine for the whole Soviet Union in Ukraine and Kyiv solving, let's say, 50 operations per second. And you have a bunch of tasks around, like ballistics tasks. US has very ballistics tasks as well. You can read the history of US computers and what mathematicians were doing on the both sides of the Iron Curtain. Some nuclear tasks, some civil tasks, and so on. Just to mention some of them, for 1952 and 1953, those years of operations, there were problems of like statistical acceptance control, determination of electrical power system stability, thermal stresses in building structures, geodetic observations, volumes of earthworks for design of road in Soviet Union, optimization of the high voltage power lines passage, of course, external ballistics, nonlinear mechanics, and thermal stresses of building, and so on. You can hide it, like hydrogen bomb behind even of some of them. And in order to understand the calculation, there was, let's say, the institute where the problem was set, let's say, for ballistics or road buildings. And that problem should be translated to algorithms that are translated to the machine calls of that first machine. And there, of course, was a queue of scientists willing to solve that machine, use that machine to solve their tasks. So you can like imagine the level of prioritization you should have at one machine in the country to solve all like important tasks. So it's like dispatching all this in time and everything. And to a certain time in the future, tasks were assigned by the highest level, like the government in Moscow. So the machine time was strictly limited between very important, like military and so on tasks. But it was just not easy to get your tasks done on that machine. And of course, you need to explain that this machine is worth it. Let's go. It was. Let's look who has done all the job, who was doing all the job. At the 8th of March, we celebrate the Women's Day all around Europe. Of course, in Soviet Union, it was well accepted. And you can see female programmers and their assistants who were using calculating machines like Rheinmetall calculator, so on, for calculating like control points to see that the digital machine is calculating correctly. You can imagine 1951, a lot of fun because many people were young. They were just graduates from universities in Malta. And you can imagine they met graduates from university in mechanics or something, engineers in electrics. So it's well like a very energetic community building and servicing that machine. Like as well, some people have named that place as a Kodlo, the place where we could kind of playfully work with that machine. You can imagine like security measures to the first machine in Soviet Union running when the hair was running inside the building because it was not far from the building, and they had fun catching the hair or trying to find it. So later security was imposed when the government accepted the machine and started sending tasks. As well, people share their memories about Yurii Yushchenko and Boris Nedenko, the mathematicians who were behind some calculations or preparation to programming. Because the first programmers were mathematicians. It was like mathematical task to do something with this machine to get results. Now we have a very nice slide saying that here there is inspired, the idea of constructing some advanced soldered interchangeable memory is important. We will not be that much on it now, maybe in the next speech next time, but here is the abstract from the book saying that the MEOM architecture inspired the address of higher rank 2 and forward. That means in modern term pointers. So working on this machine, limitations on this machine, and the ideas of the mathematicians who were working on this machine finally brought to the invention to very important. And that time it was 1955, I think, that we were testing it in hardware. So specifically, techniques such as 2 and 4 involve the use of second-order indirect addressing for intermediate structures in data shuffling. This method, known as modulation of pointers, served as a key innovation in the MEOM computer's operations. The idea of changeable soldered memory blocks raised from MEOM because it has part of the memory with plugs. Later, these plugs were made, let's say, boards with fixed soldered connections, which represented bits of the command codes for some subroutines like sines, cosine, or logarithm on everything. So you wouldn't do manual play and make errors connecting necessary plugs and so on. And that was kind of a step forward, and as well a limitation. They were hard-coded. They didn't have a kind of instruction counter. So there appeared a need to create something that was working with kind of soldered memory. So that limitation, only one subroutine level, led to new ideas that required a stack creation later and brought programmers to the pointers invention. As well, we go to the heritage of the MEOM machine. It includes some conceptual breakthrough, the idea of creating a programming program. As machine has a command of adding commands, kind of, we would say adding addresses in the memory. So it allowed to virtually work with part of the memory as a separate memory, changing it, and using another part of the memory. It's kind of stable. So that created the idea for Yurii Yushchenko as a mathematician programmer, as well as Alexei Lyapunov, the greatest mathematician in Soviet Union, working on that machine together in a period of time. That these add commands instruction allows kind of dynamic program modification, suggesting some fundamental capability of programs to alter commands and generate new programs during their run. This concept of a program in program, PP we would say, PP in Russian and Ukrainian, emerged uniquely in the USSR later, replaced by foreign terms like compiler, translator, and interpreter. In contrast to compilers in other countries, which primarily involved recording mnemonic codes into machine codes without direct involvement of a central processor, like keyboard codes or something, the Soviet PP focused on translating high-level programming language instructions into low-level machine instructions with active participation of the central processor. This innovation underscored the MEOM's impact on programming methodologies and laid the groundwork for advancements in programming languages and compiler technologies worldwide. The Lyapunov operator programming, you can see now Alexei Lyapunov photo, as seen as Moscow's developments for the Strela computer later, marked a significant milestone in computing history. PP1 and PP2, 1954-1955, represent the world's first implementation of high-level programming language. This groundbreaking achievement is acknowledged by the museum in Silicon Valley as evidence in their timeline of the history of high-level programming languages. Despite this remarkable accomplishment, these programming languages were not widely adopted due to the limited production of only 7 Strela computers and their reliability. Additionally, energy consumption of these computers hindered their widespread usage. The universal asynchronous computer, Kyiv, which was followed, introduced a significant innovation in computing with its asynchronous operation and parallelism. The parallelism was integrated into the computer's command system, leading to the incorporation of features of high-level programming languages to determine the feasibility of execution certain actions independently and or asynchronously from other, essentially incorporating means of parallelism into programming languages. This development laid the foundation for the parallel architecture not only of Ukrainian computers, but also Soviet computers more broadly. It represented a pivotal advancement in computing technology, paving the way for more efficient and powerful computer systems capable of handling multiple tasks simultaneously. Universality or versatility. The purpose of the common system was to take into account the needs of programmers as much as possible. So to simplify the programming process by bringing commands as close as possible to the high-level programming language. You can imagine mathematicians working on MEOM were in touch with engineers building MEOM, and they moved forward to the next machine. They were trying to fix everything from the point of view of the mathematician. And the mathematician's point of view was like, they have a bunch of models. They use a lot of different mathematical instruments like differential equations, like functions, like integrals, and so on, like different tools from mathematics. And that should be probably used in the future. That was not in the first machine. So that architecture for the second machine needs to support that kind of idea. So now we come to the moment, very important, but first it started from the engineer, from electricity, something, tasks, so on. Then it is switched to the programming tasks from mathematicians. And those mathematicians started thinking kind of more widely. Let's go to more mathematical instruments and help them to be embedded in the architecture. So it was a unique move in both sides, like hardware and software, to one point that was able to model a lot of math tools. Actually, we would say 80% of we have now in our processors. Now, the Kyiv computer is the first computer in the world with implemented hardware actions with pointers. The Kyiv computer is the first computer which, unlike its peers, was designed not only for mathematical calculation, but also for solving logical problems, and we would say problems of artificial intelligence even, for managing technological processes, for implementing different information systems. It represents a significant improvement and development of the unique features of MEOM computer, which started in 1950 in Theophonia, full operation. On the Kyiv computer, in addition to mathematical problems, the following problems were solved using the addressable programming language invented. Recognition of printed and handwritten letters and numbers using machine learning methods. Recognition of simple geometric figures. The Kyiv computers showcase its pioneering capabilities by tracking a diverse array of tasks, including handling informational tasks as relational database autodirector, enabling remote control of steel melting process for industrial operations in Dnipro in Ukraine, automating the design of electrical circuits for industrial households, and so on. Many of these tasks were executed on a computer for the first time globally, underscoring the Kyiv computer's groundbreaking versatility and innovation. Moreover, the Kyiv computer achieved another milestone by developing the first world emulator of another computer, Dnipro, using addressable programming language. This emulator facilitated the implementation of an addressable programming language compiled for the Dnipro computer. Sergei Lebedev, along with other engineers, leveraged advanced technical solutions pioneered on the second machine, such as dynamic address modernization, address language tool, in subsequent computer models like M20, BASM3, BASM4, as well as in other computers like Promin, Dnipro, and Mir series, as well as those in the Ural and Minsk series. A second copy of that kind of heritage of masonry of the computer Kyiv found its home at the International Institute of Nuclear Research in Dubna, Soviet Union, where it played a crucial role in solving significant problems, including particle interaction modeling. The Kyiv computer served as a foundational platform for designing subsequent computers like Dnipro, Promin, and the Mir series. The hardware implementation concepts of high-level programming languages in Promin and Mir computers stemmed from the innovative ideas pioneered by the Kyiv computer team. And the Kyiv computer team was exactly the Madsen computer team building the second computer left on their own. Okay, now we see just a fresh introduction to pointers. Let's move a bit. So, the machine itself, MEOM, contained hints for the future development and brought the idea of pointers that allow to use lists and complex hierarchical structures. And the hardware of that machine, let's say the second one, was later found in its ideas in a lot of hardware of the USSR computers. You can see the flashing theme like MEOM inspired the PP1, PP2, like first compilers, inspired the second computer Kyiv, 1956, which introduced the address programming language, which started using pointers. As well, it was used to build a new computer, Dnipro, using like we would say cross-compiling, and another series Mir as well. So you can see the profound impact that Madsen has on other machines. Let's go further. And the software world, sometimes it was assumed that software is kind of less hard, and then now you know the cost of software, and you can know the cost of hardware, you know how much cloud rent is for different cloud providers, you know the real cost is now. And then for those times, you will see that engineers were receiving, let's say, 4,000 rubles, and the programmer who was doing all this programming tasks was receiving 1,000 rubles. So it was like 4 times less salary for doing this intellectual job until let's get some recognition. You can see famous USSR figures like Anatoly Kitov and Andrei Yershov, Anatoly Kitov associated programming approach was introduced involving indirect addresses of higher rankings, pointers, and list chains. It represented a significant advancement in software development, particularly in managing complex data structures and facilitating efficient memory utilization. Andriy Yershov's alpha system further built upon the concepts introduced by Kitov, incorporating small indirect addressing of higher ranks and list chains. This system was specifically tailored for use with BEST-4 and BEST-6 computers, enhancing their capabilities in handling data structures and memory management. And autocode programming language emerged as high-level programming language that incorporated low-level assembly tools and were machine-dependent. These languages, including various iterations of autocode, offered powerful address manipulation tools, including robust support for working with pointers. These software developments, inspired by the innovations of the, let's say, second Kyiv computer, contributed to the evolution of programming languages and software engineering practices in the Soviet Union and beyond. They enabled programmers to tackle increasingly complex problems and leverage the full potential of emerging computer systems. We are very close to the end, kind of. Let's see, this is a list of publications just to see the years, like 1952, Lebedev, Sergei Dashevsky, Lev and Shkabara Ketrin, chief engineers that built the first machine. Like next year, 1952, the book was published, kind of like strictly secret book for the Soviet Union for the first machine built. And the next year it was published it was translated in US for like various security services. So it was strictly confidential book that was not introduced in Soviet Union in other institutes and so on. You have the book dated 1966. It is called like Kyiv Computer Mathematical Description. If you would go deeper here, there was like party nomenclature approach. Then if you are not the inventor, you can steal the invention being the chief kind of. And then others, if they are not loyal to the chief, they are not loyal to the party, they are kind of under press. And this type of managing innovations pushed out a lot of engineers from this team and delayed the publication of the first book introducing programming with pointers due to the, let's say, interpersonal kind of ambitions of some leaders that were focused on their like fame and so on. That's why we can see publications that were pre-printed 10 years earlier and finally printed in 10 years after the delay. Let's go forward. We have 1962, the computing machine Kyiv description, and it was translated in French, and it was translated in the US, and it was translated in Germany, in Hungary, and Czechoslovakia, and so on. As well, and 1963, the Soviet cybernetics technology, some programming elements you could find there. So you can find some links and probably you can have an access to some libraries and find them. We can share links probably in comments later for this presentation. In order to preserve the legacy, kind of computer museum is a good form, but in order to show the best minds now that the pointers were available in 1955, 1956, before them being printed in 1960, it's hard work to call and interview the real characters, the real heroes who did like paperwork, who read the preprint, who fixed mistakes. And then it's quite hard using the unique terminology that was introduced kind of in isolated environment from the Western world and so on for a period of time to describe that in the modern terminology and show that ideas were, they are provable and despite the lack of publication, despite of some press from communities, mode, and so on, the achievements were made. So a group of enthusiasts from different organizations, including universities in Ukraine, they made some measures, some restoration efforts. The group is working on restoring kind of glory of the Kyiv computer, reconstructing its kind of literally hardware and software components. The software emulation has been developed and allowing programmers to write and execute programs in the machine commons for the original computer, Kyiv. The emulator provides a platform for studying and experimenting with the capabilities of the Kyiv computer in a virtual environment. There were done some interface enhancements and continuous efforts on the way to improve user interface with the emulator. There were done some compiler developments. Work is ongoing into implementing addressable programming language compilers and modern programming languages such as Rust and Haskell. These compilers will enable programmers to write programs in a high-level language that can be translated into the machine commons for execution of the Kyiv computer emulator. An open source collaboration, the emulator and compilers are openly available on platforms like GitHub, allowing collaboration for programmers worldwide. This open approach fosters community involvement and ensures transparency in the development process. Undertaking these measures, the group aims to ensure that the available legacy of the MEOM computer, particularly the second Kyiv computer and the addressable programming language, is preserved for future generations to study, learn from, and appreciate. Now we'll go on to the thank you slide. When you see Yurii Yushchenko, Oleksandr Bezrukavyi here, I would say a couple words on the destiny of the main heroes. We could share their slides lately with links for the sites that say on their story. Sergei Lebedev was moved to Moscow to build the second big machine that was calculating as well a lot of nuclear calculations, so on. A lot of tasks were transferred from MEOM to Moscow to teach those programmers how to work with them. A lot of tasks were solved on MEOM, and that inspired mathematicians to develop the language with pointers. And a lot of people were trying to prescribe themselves the achievement of making the programming language. For example, we would see academicians who would write in memoirs like, that was my idea that I proposed, and so on. And you would check the journal of tasks solved, and you would clearly see that Yurii Yushchenko was doing 8 or 9 of the 10 tasks on that machine. So that clearly suggests that the one who is kind of guilty for inventing the language is this person. Then the next engineer, we would say, Katerina Shkabara. She worked until the tough leadership of the new chief, Viktor Plushko, and she was strict in her suggestions and moved to the team of the best cardiac surgeon in Ukraine and moved to build the first cyber diagnostic machine for kind of diagnostics. They managed to get 80% precision with perfect cards. It was not enough, but we managed to formalize the data structure for kind of diseases, diagnostics, something. And her daughter saved the legacy in the form of the website. Unfortunately, she has passed away. But we managed to talk and preparing the research for the film with her husband, and there is a website containing memoirs of Katerina Shkabara. The link will be provided later. And then I was getting a consultancy from the script consultant. He told, I can find Yurii Yushchenko, but I cannot find English sources for Katerina Shkabara, the first kind of engineer next to the Lebedev. That is the legacy now after Soviet oppressing system, looking at the Kyiv achievement, not as a very famous one, because it removes kind of fame from the central controlling part. And the local management was more interested in promoting their achievements, not the private team. So there was kind of a conflict of interest. and that pushed out a lot from the first team. And then let's move to the Lev Dashevsky. His story as well is interesting. He was a great engineer, but the new chiefs suspected him on the violating communist moral, like being in contact with a lady while being married himself. Not proved, accused, using the vote of the majority as a tool to remove all the team. That was the tools that were around an atmosphere that was around the team after. And Yurii Yushchenko managed to find the vice position with great respect and managing the team of, let's say, half of the programmers of the whole, let's say, laboratory workers. Due to respect to her and her influence, that protected the person from repression from the new chief and command. And I would say till now, the pioneering award to be awarded for achievements as a pioneers in IT. There is still an argument from an ex-management team that there is no place on the building, there are no money to fix the plate or something like that. And that's like just talking with some other guys. But that's a part of the real human story, then you will find conflicts everywhere around. And it's a great achievement that they made. And that makes a lot of interest in their kind of destinies. You can compare with US and British histories. And we have a unique opportunity to share with you the story. And thanks to my consultant or a friend, Yurii Yushchenko, who found the time and shared some proved factual material that is from different sources compilable. And due to some filters, it's now like just a job to filter a lot of online publications and memoirs just to connect points and to find the truth as much as it could. Thanks a lot. I think that's all for my part of presentation. Let's move to Yurii, and there will be open to questions if there will be time. Thank you everyone for your attention. Thank you for your interest.
Okay, thank you very much. That was great. That was a lot of information and concisely presented as well. I think I was interested, fascinated to learn about the legacy there as well. You were talking about the attempt to get the name out there and to kind of remember what people had done. One question I had, I guess, was what's been the reaction to the innovations that the machines responsible for, such as, you know, the influence on programming and on languages and on all these innovations that came from the kind of associated Western computers as well, such as, you know, pointers. Has this been do you find people are do you find they want to stick to the narrative they know, or do you find people are willing to change or refresh their understanding of history based on the information that you present to them, you know, such as you had this evening?
Yeah, we contacted the world-level expert on the algorithm, and we provided the information about the pointers invention and the translation that was available in US. We contacted the military base in US to get the translation. It was public available. We shared the path thanks to them. And the reaction was like the publication dates for the existing sources online, they were earlier kind of than the publication date, let's say for 1 year, for due to this changes in the management and communist position, so on, so on. So it is our work to find like documental proof, unless we have like oral kind of memoirs of live team members, calculators, women, who were doing some translation with the book containing information about pointers. So now it's a job to show the world that pointers invented due to the MEOM limitations later were implied like deployed in Kyiv architecture, and it was in the book that was prohibited to be published in Ukraine by Ukrainian kind of university due to the connections of the like Communist Party nomenclature or something management with each other because of the fame not being a priority for them, so on and so on. And yeah, actually, it's a good challenge to describe it more clearly. So we would like to share this information more, and this is a good opportunity, and I think that would deserve an extra, it deserves an extra effort to show that.
I was going to go right, I want you to go right back actually, if you could tell us, a fascinating challenge in terms of just the build of the first system. You said people were going out and buying the valves themselves. We do have there's stories here around our own early large computers, such as Colossus. There's a myth that Tommy Flowers, who was responsible for Colossus in the UK, went out and financed it himself from his own pocket. You know, it's highly contested history. What was the people working on the system there in Ukraine? How are they, given the supply issues post-war, the communist restrictions, the communist system? How easy, and you're talking about a computer with 6,000 valves, just the valves themselves. How easy, do we know how easy it was for them to come up with this stuff? To what lengths are they going to try and just find valves themselves?
Okay, let me say it.
So we lost, not getting you there, Yurii.
Yeah, we're here, I'm translating. Due to the fact that it was to be kept secret, because if Lebedev would promise that he built the first electronic machine and he fails, he spends a lot of state money, and there were no warranties that the machine would work as intended. So that would be in Stalin times, money expenditure, which wasn't worth. And you can imagine the jealousy from, let's say, older engineers or older scientists. Lebedev was one of the youngest, even one of the most youngest doctor of sciences. So there was a huge risk that if he would fail, that would be like close to the enemy of the state. So that wasn't like they bought things only for their money. There was kind of the project in the Institute of Mathematics run that was connected with some military calculation, let's say ballistics or something. So Lebedev was able to connect with the chief of the project, Wyshynski, and imply that some modeling of this kind of modeling device or maquette will be done for these mathematical calculations. So we managed to switch part of the government money, let's say, we would say not for purpose, but it was hard to say that it's not for purpose. So, and then if it was limited and we couldn't find it, that's the thing. After the World War II, some German factories were moved to Soviet Union, and engineers moved as well. So there was availability of lamps and quality lamps. So in terms of hardware, they could find them, and probably that was not the main part they spent their money for. It was probably maybe replacing parts, or like some part of the project. But that shows the level of their dedication and so on.
And what was the level of demand? I mean, you mentioned there that Moscow, once the machine was running, it was Moscow was saying who could use it. What kind of, in the UK, for example, we know that one of the early computers, Leo, was under such intense demand. It was built by a private company or sponsored by a private company. Eventually, they started leasing it out to other customers. And from that, they built their own business, leasing these computers to people. Do you have any sense of how much demand there was, where it was coming from? Were people being told to get in a line, take a number, get in a line to use this system? And was there much word of mouth around it at this time?
Yeah, that's a good question. There was a lot of math tasks around. You can imagine the huge country like Soviet Union or any country like Britain or any other country statistics and so on. We can remind ourselves when there is a book about calculations during the Great Depression in US. So we gave a job to people just to calculate some form, like tables of functions from math, and hundreds and thousands of people were doing a lot of things, and that was not enough. So a lot of calculations, and there was a challenge of rebuilding the country after World War II. It's a good question about how the tasks get to that machine. First, mathematicians who knew about that machine because it was not shared, and then the government who was assigning a responsible for, let's say, for this machine. Let's say the chief of the Mathematical Institute of Academy of Sciences of Ukraine, or the chief mathematician of Soviet Union. So they would solve the task. It goes to this slide. There were tasks, and there were like several different institutes involved. So that task was given by that institute. That task was given by that institute. And the question, of course, there was a lack of computing resources. There was like another type of economy, so they couldn't kind of lease it for calculations. There wasn't a commercial something, and there was a huge, let's say, military interest to any calculations, and huge priority to the military calculations, and so on. So managing priority of tasks for that calculating machine finally gets to the government of the Soviet Union, and that was there are stories like that mathematician has got this machine for the whole calculation period, and they manage the Sergei Lebedev as a team lead, or let's say the designer of this project, wasn't happy that his machine is running just for another project, not for solving the things that are important to them. So they managed to solve tasks after kind of official running times, and it was kind of being serviced, so during the time that is not at night and so on. It's a good question. We would discover further how did they manage, but for my scientific supervisor, whose scientific supervisor was in the team of his first MEOM builders, there was a rule that the task would go just after improvement from the highest committee from Moscow. And later, the Lebedev moved to build a bigger machine in Moscow that was capable to run faster. And until it was built, that machine was servicing. And then all, let's say, libraries of programs moved to the bigger machine, and for it they were spread and so on. So I don't think there were like leasing, and that is like interesting. I would say the distance from the communist center would decide where is your task in the list of priorities. So the ones who were closer, the military ones, the special services, something that would influence. And you would see similar probably things in US and UK. If it's nuclear calculations, Soviet Union does nuclear calculations. If it's ballistics something, then you have ballistics something. And there were forecasts as well.
Great. And just final question, do you think, how did it, as we know the history of computing, but was there any sense of from the officials, whoever they may be, that this was the future? They now had to start dedicating money to building more systems like this. Obviously, you had the second version of it came along some years later, but I'm not aware we saw a commercial development in what was then the Soviet Union of, that we saw here, but were officials, politicians now wising up to computers, or was it very much still much a kind of a niche activity as far as they were concerned? Some other departments' problem to deal with, or to advance.
Yeah, just this machine showed the capacity of solving military tasks. That means military money that was directed to, let's say, military department could be moved or streamed to the, let's say, computational powers. So that means teams of designers could get money, could get machine produced at the factory, let's say, like an industrial machine. So it could be spread. So that meant immediately that it's like financial success. So immediately the kind of competition started, and there were games like one ministry would have its own institute designing their own machine. At the same time, the more advanced machine would be lack of parts, and that industry wouldn't provide parts for another machine because they were competitors. And if it would be first, they would go first to the industrial production, commercial kind of. So that would mean any money would go to them. So even if you would read memoirs of people who were jealous to Lebedev, they were saying like a lot of other people, or let's say communist like management team, I would say, let's say not communist party something, but let's say like ministry management or institutes management were eager to get money, let's say for anti-missile programming kind of. So in order to do that, they need to prove they have a product, they have engineers, blah, 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 and they can provide something successful. So if that's a ministry, they have a budget, they have everything, they can easily show they are staffed, they have everything, they have a project, give us money. And then it comes now to competition, how to get that money, how to improve. Immediately it becomes not just the fair fight between, like, I would say, competition. Because that ministry knows that guy better in the party, so that would be close ties, and that means more money here. And even those who are jealous, I was reading yesterday some memoirs of the guy who was just completely incorrect about Lebedev. He recognized that Lebedev was not in bad gains of making some other person bad or something for the money. He was very wise, sustained for a long time, building kind of very wise relationships, connecting some leaders to the team in order to get the project done. So that was just very disturbed kind of commercial competition. But in terms of earning money, later the Institute of Cybernetics was built on it in Kyiv and became kind of the first in the Soviet Union semi-commercial organization that could earn their own money for their job. So it was not going to the ministry and part of it to the budget. And they could earn money, let's say, selling first computer first for them to the nuclear research center in Dubna. So a lot of money from the nuclear industry would go for that machine, to that cybernetics institute. And they deserved it. They built the Kyiv machine, they built the team of programmers, they built the advanced world kind of first point or some program. So it was really a working and breakthrough machine. So for that thing, they received money, they could hire more engineers, they could grow, they could provide them better life conditions, involve some like buildings built and so on. So that became kind of a small Silicon Valley, so you could go in the team. But now it goes again in the context. You have a management, you have their view on their kind of growth, personal in that story, being famous, proving that the institute is worth money, that the projects are worth money, and finally that came to that money earning thing as well. So kind of.
It's a fascinating dynamic, a lot of politics and a lot of sort of, as well as the economics of the case, the politics of the development is fascinating. That's been a great, incredible presentation. I'm glad we managed to make this happen. There's a lot of, I find the information out there about MEOM is quite scattered, and there's a few pieces out there which kind of repeat the same information. So it's good to get. I'm glad you were able to pull this information together for us and to do a great presentation. So I'm just going to say thank you both this evening for your hard work and for making this happen to us. And before everyone goes, don't just slip up. Before you give a round of applause, come back again, because we've got a follow-up from your colleague on May the 15th as well, I believe, haven't we? And he's going to be taking us forward a few decades to sort of talk about Ukrainian personal computers in the 80s and the 90s. So we're looking forward to that as well. And that's on May the 15th. But thanks, guys, and hopefully we'll speak to you again soon. We can collaborate again.
Thank you a lot. See you.